As compared to the Cretaceous, the Permian extinction was far more severe. Only it's not so well known because dinosaurs are considered to be more spectacular than trilobites, for instance. So that's why the Permian extinction, except for people from the city of Perm, of course, is not so famous. But of course there were, if we look at different times, there were characteristic organisms dying out. For instance, at the end of the Ordovician, the reptiles disappeared. They were filter-feeding animals, and in a far distant aspect related to vertebrate organisms. But since you are studying paleontology, I think you are familiar with reptiles. And of course the trilobites died out. This is an example of it. 75% at the end of the Devonian, so there were a lot of crises in ecosystem during the history of the Earth. This is another example, a strange tabulate coral at the end of the Perm. And this animal also, it's an interesting animal. The first vertebrates with a mineral skeleton, and perhaps you know that conodonts, the character of conodonts is relatively recently known. I have known geologists, stratigraphical geologists, who were dealing their entire life with reptilite remains, but never knew during their lives what a reptilite was. But they died before this, so it's not frustrating to them that they didn't know about it. We will look at that later, and I will look at first at the Cretaceous, at the end of the Cretaceous. This is an interesting mammal from the end of from the Cretaceous period, because although it's dinosaur time, there were already mammals, and considering its size, 1 meter in length, that Leponomalus was quite a big animal. But as you know, the end of the Cretaceous is famous because these guys, Louis and Walter Alvarez, discovered something important at the KT boundary, or KP boundary if you like, in Gubbio, Italy in 1981. And that iridium anomaly they found. Here there is a graph of the iridium abundance in parts per billion at the KT boundary. And you see that there is a peak of iridium. And perhaps you know that iridium is on Earth extremely rare, but it is it's in a way an extraterrestrial element. And there has been projects, scientific projects, so-called deep sea drilling projects in the 80s of the last century. They have drilled holes in the bottom of the ocean everywhere around the world, and everywhere where they reached the KT boundary, there was a iridium anomaly all over the world. So that makes that you think that there was an extraterrestrial cause for that iridium peak all over the world. By the way, because of this, it was possible to link the extinctions of terrestrial vertebrates, like dinosaurs, to link them between the extinction of marine plankton. And if you can link these events, then it is logical that they have a common cause, that the extinction took place at once, at the same moment. And perhaps, are you familiar with this? I think so. Everybody is familiar with this? Yeah, okay. So I don't have to explain this further, but the interesting thing about this, that this impact crater was discovered by accident. People who wanted to find oil, that's often the cause of finding interesting things, that people want to find oil, and by that project they found this anomaly in the bottom, in the sediments of in Yucatan Peninsula of Mexico. So it is generally accepted that the impact of that meteorite was the cause of the extinction events. Perhaps you have heard from so-called Deccan traps in India, has volcanic deposits, but it's also possible that the shock of the impact of that meteorite in Mexico triggered volcanic eruptions in the Deccan traps in India, so that these phenomena work together in order to initiate an environmental crisis that almost destroyed all the ecosystems at the end of the Cretaceous. And I don't know if some of you have been in Limburg, the province of Limburg in the Netherlands, near Maastricht. Maastricht is the city with Cretaceous deposits which gave the name of the Maastrichtian. Here you have some Cretaceous outcrops near the city of Maastricht. And there is actually a cave near a small village near Maastricht, near Geulhem. You see a section where the Cretaceous sediments stop, and then you see John Yacht here. Perhaps some of you know John Yacht. John is the husband of Elena, and he's pointing at a clay layer, and that clay layer is indicating the Cretaceous Tertiary boundary. So the ceiling of this cave is Tertiary. And the wall of the cave where John is pointing to is Cretaceous. And here there is no iridium anomaly, but it can be washed out. But what we see here is a crisis in the abundance of foraminifera. So the typical foraminifera, of the planktonic foraminifera of the upper Cretaceous are there, and in the clay layers above it, they are disappearing. So we do see here the effect of the end of the Cretaceous crisis. But how do we know that it was a crisis, an environmental crisis involving ecosystems? Well, that is the place where biochemistry helps us. Are you familiar? Is everybody familiar with this? I think so. This is the normal carbon stable with 6 neutrons and 6 protons. But there is also a 13 carbon which have 7 neutrons. And of course, the 6 protons is what determines to be carbon. If there are more protons or less protons, it's no carbon anymore. And why is this important? Because we can use a ratio in rocks, in fossils. We can use a ratio between carbon 13 and carbon 12. And it's compared with the standard. And if you study sediments, if you study fossils, microfossils in sediments, and the ratio, the delta 13 carbon is changing, that is an indication for the changing of environment, because living organisms, plants for instance, if they incorporate carbon through carbon dioxide, they have a preference for carbon 12. If every life form is doing fine, if the plants are doing fine, relatively much carbon 12 is incorporated in the tissues of plants. So that means that the ratio of 13 carbon is high. So the higher the carbon 13 ratio, the better life forms are doing. They are doing well. And if we look at this, if we study Cretaceous deposits, if we study the KT boundary. This is just a random case, this model, but this is based on several sections all over the world. So this is average. Then we see that iridium anomaly at the KT boundary on the right, and then we see that a strong decrease at the KT boundary, a strong decrease in the delta 13 carbon, because when the environment is in crisis, plants are not doing well, so the selection of carbon 12 is not taking place. So the there is relatively more presence of carbon 12 in the atmosphere, and that's why the delta carbon 13 is decreasing, because the ratio is changing. So this is a very elegant way to actually see a crisis in a paleo environment. And if you look at other examples, at other extinctions, you see, in a way, you see the same. If you look again at the conodonts, you can analyze their dental elements. It was quite complicated, as you see, and perhaps you know, how is it called again in English? This little creature. It's not a it's
Lancelet.
Lancelet, huh?
Yeah, lancelet.
Lancelet. So you could, in a way, you could compare that conodont animal with the still existing lancelet. It's in a way a very interesting organism, because it is in a way a model for the first vertebrate. You could call it a worm with a spinal cord in a way. It's also segmented. Our ancestors were segmented as well. It's interesting. And a souvenir of that is our vertebral column, but that's another story. But if you look at the Triassic Permian-Triassic border, which was, as we just said, also a very important extinction. And then we see, in a way, we see the same thing, we see the same phenomenon, we see that the delta 13C is going down. So if you look at the biochemistry, you see a decrease of the carbon 13. So another clear example of a parameter of the environmental crisis. There is another less well-known extinction event that's about during the Cretaceous. Perhaps you know that the ichthyosaurs died out, and it's about the Cenomanian-Turonian, if I'm correct. And so these marine animals who were dominating the oceans were replaced by other marine reptiles. When the ichthyosaurs died out, there were another type of plesiosaurs coming, and the mosasaurs evolved. They replaced, so to say, the ichthyosaurs. So the crisis was, it was about Albion and Turonian, more or less. You see, the arrow where except for Platypterygius, all the ichthyosaurs died out, and they were, as I said, replaced by all kinds of mosasaurs. And so there was also an environmental crisis in the Cenomanian-Turonian border, and you cannot only look at 13 carbon, but also to oxygen. The normal oxygen is 16O, 8 protons, 8 neutrons. That makes oxygen. But you have also oxygen, so-called heavy oxygen, because it has more mass, so hence the term heavy oxygen. Instead of 8 neutrons, there are 10 neutrons. And this is also a tool with which you can measure environmental crisis. And the point is that this is the formula of, there is a standard, yeah, you could say a monster of water, what is kept in Vienna, and that is compared with other sections, and then you get that ratio between the normal oxygen and the heavy oxygen. And if that is changing, then you have also a parameter for changes in the paleo environment. And why can we use that? That is because that the shells have mollusks have a preference to incorporate heavy oxygen in their shells, and that trend is even stronger if it is in cold water. So in cold water the ratio is higher than in water, in warmer water. And so you can use that also as a tool to measure possible crisis in the paleo environment. And if you look at the Cenomanian Turonian, you see the effects. You see the cold events, and after that you see just above you see an enormous change in the delta of 18 oxygen. That's the red